Hi, hello. Hello, everyone. Just several moments and I'll start my presentation. Uh, Hi, everyone who will be watching this um, in record, and maybe hello, everyone who is watching it online. Uh, I hope everything is okay and the sound is good. At least it works because now who knows what the internet is, right? The internet can lack here because it's not my own internet. I am in some hotel. Maxim Volkov is writing hi. Hi, Maxim. Nice to see you. Mhm. I think we need several moments. Well, I've seen some interesting approach to starting on time. Some person recommends to say, I respect you for your on-time presence, and other can catch up when they come. Yeah, this is an approach to thank for people to be on time and to start immediately. If you agree it's a good approach, we can start, or we can just chat a little bit. At least please write if the sound works. If no lags are there, I'm not sure. Yeah, the stream will be in English, yes, and um, this is unusual for my channel, but that's just for today. Um, I see the stats are okay. Seems the stream works. Maxim is writing sound is okay. VN is writing sound is okay. Okay, all right. So, all right. Hi again, I'm Alexander, and today I want to present you my ancient technology uh, called software transactional memory in C++. Maxim is writing no lags so far, good. LZ or IZ, I'm not sure. No lags, everything is good. Oh, okay, good. Why I'm doing this? Just because, why not? The technology is only for demonstrating the approaches. It's not production ready technology, but it's interesting how we can bend C++ and how we can introduce functional programming, hardcore functional programming into it. Uh, First of all, the picture you see yeah, is a really interesting structure of the technology, and we will get back to this picture. But let me first say several words about my books, because why not? I'm writing on the third book, essentially, Pragmatic Type Level Design, and there are some ideas mm, that well essentially the technology is built on the ideas from the first two books, from functional design and architecture, but also yeah, I found many ways to utilize similar ideas on the type level. So yeah, I'm writing my third book, and hopefully it will get some attention to be useful. Well, that's probably it about the books. And let's proceed with the idea of software transactional memory. This is an approach to concurrent programming in which you have some transactional context in your application, as it could be, as it was like a database transactional context, but it's not a database, it's in your code. The idea is similar. For example, when you are dealing with transactional contexts of SQL, you want to push some queries atomically, right? So that you could query data and write data back without having inconsistent data in the middle. That's the same idea, but the implementation is very different in relational databases and in software transactional memory. Maxim is writing, maybe later, interesting to hear if anything you would do differently comparing to the original idea. Can you please clarify? To the original idea that I presented on the C++ conference 6 years ago, or compared to what? Because yes, there are things that I would make not really differently, but maybe more optimal in the same library. What the idea of software transactional memory is that you define data model. For example, it will have two transactional variables and one transactional queue, and those things could only be addressed with transactional functions. Neither functions can interfere the work of other functions, other transactions, and in every moment of time you will have a consistent data model. Nothing will be in the middle of writing when some other thread tries to read the data and therefore gets something invalid. This is a problem when you deal with separate concurrent variables such as mvars, such as well, maybe just bare mutable variables. It's easy to ruin your data when many threads are trying to do their stuff concurrently in parallel. And transactional memories want to solve this problem. And they give many other interesting properties to the code, especially functional. Being made functional, software transactional memory is very convenient. They have their own price for sure. There are trade-offs, but in general, it's a very, very interesting model of concurrency. Maxim Volkov is writing to the 2018 talk. Yep. Yes. I have a couple of new things to tell about the technology, because there are two engines in the library. The one engine I presented was built on the normal free monad, and another engine was built on the short encoded free monad, and they are very different. They are very different inside, but they have the same interface. So yes, I'll tell about that, and they have different performance properties. Yeah, this picture describes how a transaction can be rollbacked and postponed if there is some conflicting access to some variable, in this case TQ. And the STM libraries take its responsibility to manage those delays, postpones. You don't even think about stopping threads and synchronizing them. STM does it itself under the hood. And this is very convenient compared to other concurrent approaches. A classic problem, a classic task done in philosophers can show us the differences between the approaches. And you probably all know this because in every university course of concurrency, this is the main task to talk about. And you see 5 philosophers. The number doesn't matter. The idea is that they are organized in a circle and they have a shared resource between them. Each philosopher is mandated to either think or eat. But the philosopher can eat having 2 forks. simultaneously. I believe it would be better to replace forks by sticks, all right? It will be more logical, but we have what we have. So a philosopher can only eat when they have access to two forks simultaneously. Two forks near the philosopher should be free, not taken. And you can see if this person eats, I'm not sure it's who is this, then this person can't, and this person can't. They should wait. And etc. Our task is to organize their infinite thinking and eating cycle. We will do it with our STM approach and see how to organize that. So we have a model. There are 5 forks. It's very essential to make those forks separate transactional variables, hence TVAR, transactional variable. And philosophers will be accessing those forks, well, by turn, right? Interesting. We can define two transactions for taking forks and can call them from different threads. Philosopher 1, philosopher 2, and they have some shared variable. So they are in the race condition of this variable, right? Reinforced learning nuggets is writing, hi everyone, hi, hello. So our task is to define the data model and the behavior model, right? And then run it somehow. Well, first of all, this is a Haskell data model for software transactional memory. Now we need some state for forks. A fork can be free or taken. We can give a name to fork, and it has a state, right? And we define a convenient variable for that, tfork, tvar, tfork. There is activity, thinking or eating for philosopher, and each philosopher has name, has activity, and 2 forks. Okay, that's simple, and Haskell code is a little bit cleaner than C++ code. A little bit, I mean, quite a little bit. But the same code is possible to write in C++. That's my point, that the ideas can be transferred from Haskell to C++. Probably not, probably this only direction, not vice versa, but yeah. And monadic software transactional memories can also be implemented in C++ with some certain issues, of course. So we have a fork state, we have a fork, we have activity. Actually, the same, right? Well, also some pair of forks, left and right, for convenience. Okay. Now let's talk about the transactional model of STM. Sorry if you already know this, but this should be articulated, right? This is also not an original Haskell STM. It's my own implementation in Haskell, quite literally the same as in C++. What we see here, we can read some transactional memory variables with read tvar. We get what is inside. We can return data from this transactional function, and we can modify our tvars, write something into that. In this case, we can apply some function to the internals of the tvar. The whole function take fork operates inside the STML monad. It's a transactional monad. Every function that has the type STML something is our transaction, and we can join many different transactions into a bigger one. For example, read tvar is another smaller transaction, right? modified var is a small transaction. The whole code is a combination of these two transactional functions. And it's very convenient because you don't need to put synchronization here. There is nothing about threads. There is nothing about mutexes or other kinds of locks. You just read and write transactional variables like it was a regular code. Everything to synchronize them happens behind the scenes like magic. In C++, though, it's a little bit more complicated just because we don't have the do notation in C++. We don't have monads in C++ per se. Well, actually, we can implement any monad. It won't be as convenient as in Haskell, but it will work. In this particular case, I implement the same flow of working with a fork with just monadic combinators. And there are several combinators in the library to join different transactions. Because this code previously seen can be rewritten in terms of combinators, in terms of monadic combinators. So it can look not like this, although this is a very convenient form. It can look like this, or even a even more mind-blowing expression of functions applied to other functions. In this particular case, we have HTML as a transactional context, and every function that returns this HTML is a transaction. So those functions are all returning HTML, as we see. Those are variables. So these are all transactions. And for example, the sequence function takes one transaction taken by us and combines it with another transaction called pure true. This transaction just returns true. It doesn't mutate any variables. Doing the same with other functions, I can join more and more transactions into one big transaction, take fork. For example, there is a special transaction if then else. It examines the results of the first transaction, and depending on the result, either chooses to go with the second transaction or with the third one. So this is our monadic code in C++. I guess it can be improved in terms of developer experience, but this is another big topic. I've seen several attempts to implement do notation in C++. I don't think they're all any of them are successful, and they require macros and they require metaprogramming, but still. Having a smaller transaction, we can build a bigger one, right? HTML is on our sign that it's a transaction. So here I do taking forks twice, left and right fork, and then return the state of those forks. This is another transaction of a higher level. Same can be done in C++. Looks quite similar, actually. There are two simple functions, and there is a both combinator that evaluates both of them and returns their combination result. So yeah, this is how we use STM. And to achieve that in C++, we actually need a lot of internal mechanisms. Well, I have several slides about changing activity of philosopher. You can then investigate it. They're actually the same, just I won't be discussing it in details. There are several functions to work with forks and activities, and if you run the program, you will see that it runs infinitely, and some arbitrary philosophers change their activities if they can. If they can't, they just wait for their turn. And this will be the output of the program. So I want to talk more about the internals of this technology, because it was a challenge to implement it 1 month prior to the conference. And I had to invent several things in C++, especially algebraic data types and the way I need to work with typed variables. Because when we define a tvar, like here, like here, t fork pair, for example, maybe earlier, tvar fork, the library doesn't know about the user type, in this case fork. The user type can be any, right? Not known upfront. The library should allow us to store any possible value we need. It can be a simple data type, it can be a compound data type, it can be functions or classes or whatever. So this is a problem, because in my approach, I need some way to store them, those variables. In a Haskell STM, it's done differently. Every transactional variable is a storage on their own, and they do not need to be stored behind the scenes. They are kind of containers on their own. In my case, tvars are not containers. They are references, typed references to tvars, to real data stored somewhere behind the scenes, somewhere in the depths of the library. So I wanted to have them stored in one place, but I could not store types of arbitrary type, right? I cannot just have a heterogeneous collection. All the collections are homogeneous, right? I'm not sure I pronounced these words correctly, but still. So I needed to invent the typed untyped design pattern for that. I invented it a bit earlier, but it was very useful in this particular case. So I store those variables, the data, in untyped form, and when I need to deal with the contents, I restore them, and using the information provided with tvar from the interface of the STM, I can do casts from any type, std any, to the user type and back safely, because the library is built with the idea to never allow the user to request a variable of a wrong type. It's certainly possible, because in C++ you can do very dirty things, but in general it's not possible. So what's inside? There are two halves of the library. First half is the interface, monadic, free monadic interface to the STM library, and there is interpreters of this interface. So well, let's proceed and we'll see. The library mimics Haskell's STM because it's easier And in fact, this was the only way I could implement STM. I don't think I can implement it in some other form. And there are main transactions, main functions in this library: creating tvars, reading tvars, writing tvars, the retry combinator. This retry combinator mandates a transaction to stop and wait for certain variables to be in certain conditions. This means if you met some variable that has a wrong value, wrong means not the value you need in this transaction, then the transaction will be restarted and the evaluation will return to this point when and only when the variable has the correct the needed value. So retry helps us to mark certain branches of your transaction as unwanted, and when the retry is hit, the transaction will wait for something to change, for some variables to change, and then we'll try again. This simplifies concurrency like a lot, and this only combinator in monadic STMs is super powerful. It's difficult to overestimate how powerful it is. And certainly there is a transaction that does nothing, just returns a value. All right, this is the interface. But also, as we are dealing with monad, we need a binding mechanism, because this bind function is a monadic bind, and all the other combinators can be built on top of this bind. I mean, if then else, sequence, unless, when, and all other monadic functions, they all can be done with this bind to rule them all. And this is a core, a heart of any monadic code. In the HTML library, this bind combinator allows for several transactions to be combined together. This is the example of how it can be done. A new variable is created with 10 inside, and then we bind this variable, actually transaction, to some lambda, and in this lambda we are reading it and returning the result. So T2 will be a result of the final transaction, and we'll have 10 inside. So let's talk about algebraic data types in C++, because it's a pain in the ass actually. To implement one for my algebra of STM, I needed this for separate individual types, structs. They are template types, because we don't know about the user type up front, and we want to work with any arbitrary type. And there are also requirements that are coming with free monad to for these methods to have a specific shape. In particular, there should be the next continuation in every method, except the retry, because it doesn't have continuations. But this next is a function that will proceed with the next method when this new tvr is evaluated. So new tvr is evaluated, gets some result, and passes this result to the next continuation. And this is actually quite a deep idea. But then we need to combine them, to merge them in a common type. I mean, in a type that looks like algebraic data type in C++. It's a variant. It's actually a very inconvenient and a very weak ADT, or maybe not really an ADT, but something similar, but not quite. Actually, working with this kind of ADTs in C++ very painful, but we have to. Maxim is writing, interesting, uBind is a function and not a struct to be interpreted. Yes, it's a function because it's really easy to implement as a function, not as a struct. I can implement it as a struct, but the struct will have several functions, several methods in it to make everything work. But yes, it's a function that has a really difficult implementation because it has it needs to work with the first transaction somehow, and it has to work with the continuation somehow, and combine them, and also consider that the user type can change from A to B. A and B can eventually be the same, but in general, binding functions have a right to change the type. For example, we want to apply some function to the internals. For example, we want to turn an integer number to a string, and this can be done with bind. So bind changes integer number to a string, and so this also should be accounted. And not only that, but the typed untyped trick, everything should be made very, very accurately here, because in C++, any misplaced step and everything blows up. So in general, you can see that I stack all those types into a variant and call it as TMF. And also I don't just store them with unknown types. I store them as td_any. This is the untyped part of the library. And I need to take specific actions to convert to any and back. Yes, and those actions should be taken in specific places. Yeah, there is a typed interface to the library. There is some intermediate code in the interpreters, and those interpreters can cast to and back, and in any form it can be stored and can be requested from the storage when needed. This is where typed untyped design pattern works. Why it's pattern? Because I used it in various places, and in Haskell, in C++, and it works. Yes, as I said, the library has two engines. First engine is built with a normal free monad. This is how it's defined in Haskell. It's a recursive type that helps to wrap our EDSLs into a monadic form. It's quite difficult to understand what these things do here. Well, actually, you can read several materials on that, and in my book, it's this topic is described in detail. So I anyway can't dive into that. But in C++, it's again an algebraic data type made with structs, which is very, very difficult. And here you see a recursive type STM that stores HTML, and HTML stores something else. Those two variants, pure and free. This is a recursive type because there are HTML fields in HTMF. So we need to put one into another. Pure is a terminator of the chain, of the monadic chain, and free is a continuation that joins several methods together. And this is how it looks like conceptually. There is a free type that wraps our algebra method, for example, readVar, and there can be another nested free type that represents the next action, and also the next action, for example, write tvar, and finally the termination of the chain. And those chains can be combined. So if you had several layers in one chain and several layers in another chain, combining them means having all the layers in a single chain from here to here. So one pure will be replaced completely with another chain. Yeah, in general, this is how free monads work. And it can look like this in C++ code if you try to debug it and see the internal structure. It can look like this: STML nests freef, nests STMF STML, which nests readTvar, and which nests a continuation and another STML here, and etc. and etc. and etc. So the chains can be really long. And they will be long. The longer you have your transactions, the longer will be HTML chains. And it's essentially a tree, right? And what we do with trees, we visit them to make some actions. The bind function, that one function, is a visitor actually, and it can traverse chains. Traverse first chain and put the lambda inside the deepest method inside that chain. I won't show you the visitors themselves because they are mind-blowing. You can just open the repo and see the code. But yeah, this is how we do pattern matching in C++. This is the pattern matching, the bind STMF visitor, which is aware of those methods, right? And does some magic inside. Especially it does some conversion to and from std_any. Yeah, this was the most difficult part to implement in this library. Some example of the reader tvar method, I mean struct, and some method, I call it struct, but it essentially encodes the method. And this to any, a specific function to work with std_any's and convert to and back. This happens in several places, and it works like that. We have a type, and we can convert it here, and then this a type will be preserved inside the tvar. And this helps us to keep the code type safe. Need to go, we'll look later, says Maxim. Sure. Thank you for watching. Bye. Interface and implementation. Well, what's the idea behind the STM? As I said, it works differently than Haskell's STM. But it works differently by reason, because I don't think I can easily re-implement the original algorithm of STM, the original concept, because in Haskell's STM, tvars are kind of active variables. They have some journal to understand that they were changed, and to understand that there is a conflict between this tvar and that thread, and two threads can mutate tvars in Haskell in parallel, but the conflicts can be solved using various journals. In my case, it's not like that. I have versioning for every tvar. I do version control using GUIDs. This is much less efficient than the original approach, but it's much simpler than that. So my implementation is tiny, and it had, I guess, it didn't have any severe bugs. Maybe there are subtle concurrency bugs are still there. I don't really know, but my test didn't show it. But the implementation is tiny compared to the original code. So this is a way to implement STM in your language and have it right now until a more mature approach is there. So if you want to, you can take this approach and implement it, for example, in F#, in Scala, but maybe in C++. This version works behind the scenes, and I have to keep some context. Actually, it's a database of untyped var IDs and handles. The transactions work with tvar. It doesn't store data. It can be easily copied. It's lightweight. The data is stored inside the transaction. My stream says there are problems with stream, right? Well, wait a second. What is the stream okay? Can you please write if the stream works? Because I see some problems with the stream. Okay, seems okay. Let's return to the implementation. So yes, I do versioning inside every tvar, and the transactions only operate with lightweight tvar, so they can be easily copied, and they don't consume extra memory. In general, transactions should be pure, because you don't really want to evaluate any impure actions inside the transaction. Transaction can be restarted as many times as it needs. So your effect will be restarted or will be partially evaluated. That's bad, of course. For example, you can write several times into console. It's a very dangerous thing, right? You can write several times into a database or whatever effect you choose to put into your transactions. So transactions must be pure. But this is true for any functional programming in C++, in Scala, in other languages, even in OCaml, F#. You should be very careful with effects in pure code. And transactions are intended to be pure. They are interpretable chains of methods. They are not methods themselves. So this is why they should be pure. Impurity happens inside the interpreters. As I said, there are two engines in the library, and the second one works with church encoded free monad. The normal free monad, this one, has a problem. Its nesting has a complexity of O squared. I mean a quadratic complexity. When you do binding, when you do evaluation, the complexity is quadratic. This means when you merge two transactions, they will be merged very slowly. They will be joined very slowly. And this is the problem of the free type itself, the way of the free monad is built. But there is a short encoded free monad, and it has a little bit different implementation. As you can see, this one is algebraic data type with two methods, and this one is a function. It's a big function that has two arguments. Both arguments happen to be another functions, and it returns some result. This is a recursive function as well, but its internals are very, very clever. So I don't really understand the internals of this church encoded free monad. I just managed to take Haskell sources and re-implement it in C++. This is what I got. Notice that I have to work not with specific types as here, but again with any, with std any, just because that's a specific problem of my C++ implementation. Otherwise, I could not use transactional variables of any types or of arbitrary types. It would be very, very bad library if I allowed only certain types to be stored in the STM data model. But for now, any type can be stored. Well, there are some issues with storing completely arbitrary types in C++. For example, the internals of the library do some copying here to store data. So this should be taken into account, right? It's not free. Yeah, but for example, I would really avoid storing strings in STM. Maybe integers, maybe short strings, maybe characters, maybe booleans, maybe pairs, maybe some small structures, but storing big strings is a bad idea. So, for example, implementing a concurrent editor will be not very good idea with this library. You need another approach to concurrency. Yeah. So this is effectively it. And if you have some questions, you can ask. I'll hear. But that's the whole presentation. Certainly, there are even more interesting details if you want to deep dive into the idea and into the internals, into the implementation. For example, this is how looks the church encoded free monad and its bits. This is an fmap function that is needed to traverse the chains, considering that those chains are not chains but rather functions nested into another functions like here. So fmap represents another concept from Haskell, a functor, not a C++ functor, but a Haskell functor. This functor is it's an idea that if you have some structure, you can traverse that structure and change every contained value in it. For example, you can traverse lists, maps, dictionaries, and you can alter all the items without altering the whole structure. If you have a list of 4 items, 4 integers, for example, you will have a list of 4 something, for example, 4 strings, but it will be 4 items. So the fmap and function don't change the structure, but can alter the internals. This is needed for free monads. There are interpreters here, and they have some magic inside, including type level magic a little bit. There are things to I don't really remember what it does, but it does some casting. Yeah, certainly C++ is a very dangerous language, so this implementation is very inefficient, I guess, because making it efficient means using move semantics, using special values, references, and maybe thinking of less copying. I do a lot of copying here, right? just because I wanted to implement it and to demonstrate uh, a proof of concept. But this library can be implemented in a much more efficient way, especially considering current modern C++ features. Reinforced learning nuggets asks, will free applicatives along with free monads make things easier or harder? Is there any need for free applicatives? Free applicatives, I believe, have less power than free monads. Thank you for the question. Yeah, I have less experience with them. I tried to use them uh, the way I used free monads to implement some concurrency. I failed, so these my experiments were unsuccessful. I don't think they are needed here because free monads are very powerful and they are enough to implement even this complex idea of STM. There are even more free structures in Haskell and in category theory, and the whole concept of being free is a bit mystical to me because I don't really know what this means. In tutorial, we can see free monads wrap your type and give you monads for free, but that's a folklore. There are actually other considerations behind the name free. They are free in terms of some math concepts, not because they give us something in our programming. In particular, free applicatives, I guess you can implement free applicatives using free monads because there is a hierarchy of those structures. Functor, then applicative functor, then monad. And the functor is weaker one and monad is the most powerful of them. And if you have a monad, like a binding function from the library, for example, where is this? This bind function. If you have it, you can implement fmap from functor, and you can implement methods from applicatives solely using bind, but not vice versa. So if you have fmap only, you cannot implement bind using them. You need extra code on top of that. Maybe if you maybe it's possible to utilize those concepts to simplify the code in some way. I don't really know, because when you open some category theory related library in Haskell, you see how concise it is, the code. You see how clever those combinators match. I am a Barre books author. I don't know those tricks and I don't know category theory. I just can implement some stuff that works, but maybe it's not elegant as category theorists could do. Well, that's it. I think we can finish at this moment. I don't have any specific plans for the library. I just I see a lot of other ways to apply free monads, and the existence of this library proves the powerful nature of free monads. Yeah. So that's it. Thank you for watching and see you next time. Maybe I'll take it as a rule to give some talks, to stream some talks. Maybe we'll see next time. So thank you and bye.